Good afternoon, Zoom and on-site participants, and welcome to join Innovating to TechTalk. Today, we are happy to have Dr. Yu Chang, Associate Professor from Department of Mechanical Engineering, to be our moderator. So, without further ado, Professor Dr. Chang, please.
Okay, hello everyone. So it's a great pleasure. Today we will have Dr. Huang here as our speaker. So this is a TechTalk series. It is a forum and dialogues given by engineering researchers of diverse academic backgrounds to share their insights on innovation-related topics. So let me just briefly introduce our speaker today. So Dr. Huang is an associate professor from computer science. He was a postdoc at Stanford University before joining HKU. He obtained his PhD from University of Pennsylvania and a bachelor degree from Tsinghua University. So he will talk about the learning optimal auctions from data. So without further delay, let's welcome Dr. Huang.
Thank you for the introduction, and I would also like to thank colleagues from Innovating for giving me this opportunity to share my research. Today, I'm going to talk about optimal auction from data, and you can see in the background image, when we talk about auction, this is probably what you have in mind, right? Like someone auctioning out some artwork probably, and then a bunch of bidders sitting down here and then sort of raising their hand to bid for the artwork. Let me ask a question first. How many of you have ever sit in a physical auction like this one? Can you raise your hand? No, right? No one, okay? That's what I expected. And actually, even after working on auctions and related problems for more than 10 years, I have only one experience sitting in a physical auction, and that was from more than a decade ago in a cruise trip. And as a grad student, of course, I don't have enough money to actually bid, but I'm just sitting there and just to see the whole process. So because of that, auction is something that probably feel a little bit distant to most of you. So I would like to start the talk with some auctions that actually happen around us. Okay, so this is one of the CarPlay auction that make it to the headline earlier this year. Every now and then, the Hong Kong government is going to auction out some lucky car plate number. And for each car plate, they're going to start with some reserve price. And basically, interested bidders will just bid, just like what you see in the earlier slide. And then every time you raise your hand, you have to outbid either the reserve price or the current highest bid, whichever is higher. And then the auction goes on until no one is going to willing to raise a hand, and the last bidder gets the car plate at the price that he last bid. So usually the sale of price range from tens of thousands to hundreds of thousands of Hong Kong dollars. But in February this year, a lucky car plate with a single letter R sells for 25 million Hong Kong dollars, and that make it to the headline. Another example, well, one of the most important kind of resources in Hong Kong, land, is actually distributed by the government through auctions. So every year after the budget speech, the government is going to announce the annual land sale program, basically what sites will be for sale in the coming year. And the two means of distributing this land are land auctions and public tender. Now, the land auction is basically a sort of an English auction, just like the CarPlay auction and also the artwork auction in the first slide. But for some historic reason, land auction has stopped about a decade ago since 2011. And then in the last 10 years also, lands are distributed through public tender, so which is essentially a sealed bid first price auction. So what does that mean? Well, every bidder is going to come up with a bid for the land. And then they're going to submit a bid to the government, essentially in a sealed envelope. And the point here is that the competitors do not get to see what the other bidders submit. And then after everyone submit their bids, the government is going to find out who's the highest bidder and also compare the highest bidder's bid to a reserve price for the site that the government set beforehand. Now, if the highest bidder's bid is larger than the reserve price, then the highest bidder gets the land and paying what he bid. Otherwise, then all the bids get rejected, just like in this news, the Stanley side tender get rejected because all the bidders' bids are below the reserve price. Okay? Okay, some of you may say, okay, all of these auctions are happening around us, but well, it's none of our business, right? Only rich people are involved in this auction. So I would like to give you one more example that is actually everyone has experienced, but only behind the scene. You may not realize there's some auction happening here, and that's the online advertisement auction. So we all rely on search engines and use them every day. And every time we search for some product, and let's say a tablet, other than the so-called organic result, which lead you to some relevant websites that maybe sells some of these products, there are also some sponsor results, and then they're shown because these advertisers are willing to pay certain amount of money to the search engine if the user actually click on their website. So here's how it works. So after you submit your keyword, the search engine is going to figure out which advertisers are interested in this keyword. And then beforehand, the advertisers have already specified the maximum so-called cost per click, that basically how much they're willing to pay for a click to their website if the user search for this keyword. Now, in the search engine, the search engine does not simply just compare these bids, essentially. They also have some secret formula to come up with some quality score for each advertiser. And the quality score may depend on their machine learned estimation on how likely the user is going to click on the advertisement. And that's called the click-through rate, and also the quality of the website, the relevance of the keywords, etc., etc. And this formula is a secret and no one knows what it is except insiders in Google, but it is going to become some integer number between 1 and 10, okay? And after that, the search engine is going to aggregate the maximum cost per click and the quality score into a so-called ad rank. Now, once again, this formula is kind of a secret, but here, for simplicity, I'm simply multiplying the cost per click and the quality score and then raised by 10, okay, to get some other integer number. So the larger this integer number is, the more attractive the advertiser is to the search engine. And at the end of the day, the search engine is going to assign advertisement slots to the top advertisers according to the ad ranks. Now, in this example, let's say we have only 2 slots of advertisements, and the advertisers A and B will get the slots. And every advertiser is going to pay an amount that is sort of the lowest cost per click amount that will still make it win that particular slot. So in essence, the search engine is trying to lower advertisers A's bid from 0.2 to something as low as possible until, well, if you get any lower, you will move from slot 1 to slot 2. And that threshold amount is what advertiser A pays for a click. Okay, so that's an ad auction. And ad auction actually, well, attributes hundreds of billions of US dollars of annual revenue to these major search engine companies. And what its magnitude is actually has far surpassed all the traditional advertisement business like on magazines and TV, etc. combined. Okay, so these are some examples of auctions that are happening around us every day. But why should I, a computer scientist, to study auction, right? Like, shouldn't this be a business of the economist? Well, first of all, we see that, okay, there are a lot of money involved in this auction, and some of them are happening in the IT business, like the online advertisement auction. But for me, a theoretician, that's actually not the real reason why I'm interested in it. So explain why, let me explain some conceptual questions that computer scientists may ask. So quoting from Wikipedia, the theory of computation is focused on answering fundamental questions about what can be computed, and more importantly, what amount of resources are required to perform those computations. Now, some of the more commonly known examples of computational resources may be time, or CPU cycles, or GPU cycles, or space, the amount of memory or hard disk space necessary to store your data. Well, indeed, these are some of the most fundamental questions, and multiple Turing Awards have been awarded to pioneers who study these kind of questions. For example, Richard Kopp was awarded the Turing Award in 1985 for his contribution in various algorithm domains, and in particular for identifying polynomial time computation as the intuitive notion of what can be computed efficiently. And Juris Harmanis and also Richard Stearns were awarded the Turing Award later in 1993 for their seminal paper that defines the notion of time complexity and space complexity. Okay? Okay, but my specialty is somewhat different from these two. I'm interested in information as a computational resource and its role in computation. Now, although it's not directly relevant to this talk, but in all of computational problem, you need to make sequential decisions based on partial information or lack of the information about future. And that's correspond to another research direction called online algorithm. And one of the pioneers that actually investigate online algorithm is none other than Richard Kopp. So because I'm interested in information, and it just turns out that auctions is a really ideal topic to study if you're interested in the role of computation in computation and decision making. And let me give you some examples. So before the auctions even start, it kind of makes sense to gather as much information as you could about the bidders so that you can make more informed decision in how to design the auction format and how to allocate the resources to meet various goals. And there are information comes in all shapes and sizes. For example, there may be some public data set that you can resort to, and there may be some transaction histories that the users had in the past and which you have access to if you're one of these big i.i.d companies. And maybe you can also do some market survey to learn more about how users value the product that you're actually selling. Now, at this stage, we can ask some natural questions. For example, what information is important? Well, maybe some users are more important than others because they are more likely to be willing to pay a higher amount for the product. And then when you already learn a lot about, let's say, user A, which is more important, and maybe less so about user B, and now you have a budget, right? Now it becomes an interesting question whether you should gather more information about user A or user B, right? And also, you can ask how much information, how much data is required to meet a certain goal. And let's say I want to maximize my revenue and at worst leave only 1% of the revenue at the table. I want to be 99% optimal. Now, after this stage, during the auction, while the auction protocol is essentially a communication protocol where the bidders and the auctioneer communicate with each other, right? So some bidder say something and the auctioneer say some other thing in response, and this can go in multiple rounds until we reach a final conclusion and who gets the good for sale and how much the winner should pay for the good, right? So since this is a communication protocol, essentially it's a way to exchange information among the auctioneer and the bidders. And at this stage, we can ask questions like, well, how should I design this communication protocol? How should we exchange information in a way that the bidders are incentivized to report their private information or like how much they're willing to pay for the good truthfully to the auctioneer so that I can make informed decisions. And also, it is also interesting to say that, okay, how to design this protocol such that I reveal just enough information so that I can convince that the bidders that I'm actually running the auction format that I claim I would be running. And this is actually a timely question because, well, earlier last year, there has been a scandal that one of the major company actually secretly sort of twist the claim auction format and they're running something other than what they claim they should be running. And that actually make it to the headline in the US. Okay, and now after the auction, right? I mean, I have the transcript of this communication during the auction, but we all know that the bidders are willing to manipulate this communication and do not reveal their true information if they have reason to do so. Now, one reason would be that, okay, the auction is not truthful in the sense that, okay, they can game the system and basically get better outcome from this very same auction. But now, since we are also trying to learn the next auction based on user data, some of these users may realize that what I how I behave, what I report today also affect the auction format that I am going to experience tomorrow. So even if I cannot win today, I may have incentive to sort of twist my data so that I can get a more favorable auction format tomorrow. So all of these reasons may cause bidders to report sort of manipulated information during the auction format, and therefore after the auction, we have to do certain kind of modification to the data so that I can infer reliable information about the bidders for our future auction. And everything that we infer here will go back to the first stage of the next auction. Okay? And by the way, this is by no means a sort of exhaustive list of how information play different roles in auction. These are just some examples that are related to some of my own research interests, but there are actually many other topics that are interesting as well. Okay, so today, well, I just want to focus on the basic and focus on the intuitive level. So let me try to squeeze a introductory auction theory 101 into just 2 minutes, okay? So we're going to consider a very simple auction format where we only have one item for sale, and we have multiple bidders interested in this auction, and each of them has a private value, VI, which is how much they're willing to pay for this item. And then we're going to assume that, okay, this VI is drawn like independently for different bidders, drawn from some publicly known prior DI. That's a distribution. And we're going to consider a relatively simple auction format called direct revelation auction, where it proceeds as follows. The bidders first report their values, and they may or may not manipulate the report. And then the auctioneer is going to pick a winner based on the reported values. And then they are going to choose a price that the winner should pay. Now, just put it into context, we have talked about the so-called first price auction. So in the first price auction, the winner selection rule is simply choose the bidder that submit the highest bid, right? And then the price that the winner pays is actually the bidder's bid, okay? Now, you may have heard of an alternative auction format called second price auction, which has the same winner selection rule, still the highest bidder wins. But then in the last bullet, where I need to choose the price that the winner should pay, well, that's not the highest bidder's bid, but actually the second highest bid. And the logic here is that, okay, how much I pay should not depend on my bid, so that I have no reason to artificially lower my bid as long as I win the item. I mean, my payment is actually not dependent on my bid when I win, right? So I have no reason to manipulate. Okay, so these are some relatively simple auction format. But let's say you have a natural objective, let's say, to maximize your revenue, okay? Now, it turns out if you want to do that, then the auction format you should use is a bit more complicated. And this problem has been solved by Roger Myerson about 40 years ago. So what he showed is that, okay, the optimal auction is determined by the concept of virtual value. So for each bidder I, and given his bid, given his distribution, I'm going to have a very specific formula for calculating a so-called virtual value. Now, for now, it is not important what this formula is. I'm just listing it here for completeness. And then after that, well, instead of choosing the bidder with the highest value, I'm going to choose the bidder with the highest non-negative virtual value. So what this means is that if every bidder's virtual value is negative, I'm going to just keep the item on sale. And that corresponds to all the bidders submitting too low of a bid and maybe below the reserve price, and therefore I decide not to sell the item at all. And after that, the winner is going to pay a payment that is basically the lowest value below which, above which he or she will still win. And that's the same logic that I explained when I explained the online advertisement auction. I'm going to try to artificially decrease its bid as much as possible until at the threshold point that if I decrease any further, this bidder will no longer be the winner. And that's the threshold bid that the winner is going to pay as the price. Now you can see that according to this formula, we can have so-called the price discrimination, because according to this formula, there's no guarantee that a bidder with high value is going to end up with a high virtual value. So it is possible that a bidder with a slightly lower value actually wins the item. And the reason being that given the prior information, I know that maybe bidder Alice is very likely to have a very high value, and therefore when his actual value is actually on the lower end of his value distribution, I may not want him to win the item. I want him to pay a higher price in order to win the item. But there's a problem here because according to this formula, here capital Fi and Vi is the sort of the CDF function of the value distribution, and small fi, Vi is the density function of the distribution. And what this says is that we need actually fine-grained information about the value distribution in order to actually do this calculation and calculate the virtual value. And there's a question that whether we actually have enough information to implement this auction or this algorithm. And this question has actually been asked by economists even like only a few years after Meison's work. And this is Robert Wilson, a Nobel Prize winner in 2020. And by the way, Roger Meison is also a Nobel Prize winner for this work of optimal auction in 2007. So what Robert Wilson asked is that, okay, claim is that I foresee the progress of game theory as depending on successive reduction in the base of common knowledge required to do useful analysis of practical problem, and only by repeated weakening of common knowledge assumptions will the theory approximate reality. So basically, we don't actually have the knowledge of this value distribution to actually implement Meison's optimal auction, and to what extent we can weaken this assumption of knowledge and still approximately implement Meison's auction, right? And what this leads to a long line of research, and some even swing to the other extreme and say that, okay, let's go for detail-free auction and assume we have no knowledge at all. But nowadays, while we know we have a lot of data, right? Assuming no knowledge at all is a little bit extreme, and you don't want to throw away the baby with the bathwater, right? And also, people have investigated a lot of middle ground. But if we ask ourselves, okay, what's the purest form of information we could have about a value distribution, then it is a sensible conclusion that, well, maybe we have some i.i.d. samples from this distribution, and those are the only form of information that we can have. And in practice, these i.i.d. samples are, roughly speaking, correspond to the past user data that we have. And maybe similar bidders have bid for similar items in the past, and those can be viewed approximately as i.i.d. samples. And this question has been formulated by Richard Kopp and Tim Roughgarden, and they basically ask, well, how many samples are sufficient and necessary if I want to learn an auction that is, let's say, 99% optimal, or let's say 1 minus epsilon optimal for any small parameter epsilon. Okay, so even before they formulated this question, there has been some sporadic early studies before 2014. But after that, this literally led to hundreds of papers on this topic, and I cannot list all of them. Here, I just list a few what I consider to be most representative. In the first 5 years after they raised this question, they have studied this through the means of learning theory. And since 2019, the latest research has turned to learning the value distribution in particular, using the fact that they are product distributions. Okay, so in the last 10 minutes or so, I would like to just briefly go through these 2 stages of study and just focus on the key intuition behind this research. So now we need to go through the learning theory 101. While quoting from the pioneer, Vladimir Vapnik, the learning process is a process of choosing an appropriate function from a given set of functions. So in the context of auctions, then basically the set of functions that we are looking at is the set of auctions, okay? For each auction, the function is a mapping from bidder's bid to the revenue that the auctioneer gets by running that auction on the specific bid profile. And what we want, the so-called appropriate function, is the function that maximizes the expected revenue that are earned by the auctioneer. So here's the basic idea if I follow the learning theory. Well, we want to choose an auction with maximum expected revenue, right? Well, it would be nice and intuitively true that with enough samples, every single auction's expected revenue are actually close to the average revenue over the samples, right? And then, well, when I say average revenue over the sample, well, I'm basically saying that the expected revenue over the uniform distribution over the samples, and that distribution is called the empirical distribution. Now, if that's true, then we can just choose the auction with the maximum average revenue over the samples, and that's called the empirical revenue maximizer, and we'll be done, okay? Now, in this line of thinking process, The most hand-wavy part is the second bullet point. We are saying that, okay, with enough samples, well, all auctions expected revenue can be estimated by the samples, right? So in the next slide, let me go through how this is actually substantiated in classical learning theory. So let's ask ourselves a simpler question. Let's say I only have one auction and I want to estimate the expected revenue of that one auction accurately. How much sample do I need? Well, standard tools like concentration inequalities from statistics would say that, okay, if you want to estimate it up to epsilon error, then all you need is basically 1/epsilon square samples, okay? Now, well, this is a non-proof, but I don't know whether some of you have seen this. This is called a Galton board, and basically a bunch of balls are going to fall right from the middle and going to hit a sequence of rows of pegs. And every time it hits a peg, it could sort of randomly go left or go right with equal probability, and that's the assumption, okay? Now, at the end, you see, okay, where do these balls land at the end after going through these rows of pegs, okay? Now, if you imagine going right correspond to +1 and going left correspond to -1, then the end location of these balls are basically the sum of a bunch of random variables that are uniformly distributed between +1 and -1, and I'm going to label the final location by numbers where the location in the middle is 0, and then +1, +2, etc. to the right, and -1, -2, etc. to the left. And you can see that there's a curve that looks like the shape of a normal distribution, and when you do this experiment, the final number of balls are approximately this normal distribution. Okay, so basically this is saying that, okay, if I sum up a bunch of i.i.d. random variables, then the distribution of the sum is going to behave like a normal distribution. And here we are sort of, when I evaluate the auction's revenue over i.i.d. samples from the value distributions, I'm basically summing up i.i.d. random variables, and the end product, the average sum is going to behave like a normal distribution, and it's unlikely that it's going to deviate from the expectation by more than the standard deviation, and that's how you can conclude that 1/epsilon square samples are enough for estimating the revenue of a single auction. But we have a problem, right? Like we have a continuous, infinitely many auctions. So we need to have some other tricks to move from one auction to all auctions. And that brings us to the concept of epsilon ball. So we can imagine that the auction space being this shaded area, and when I estimate the revenue of a single auction A accurately, I also accurately estimate the revenue of all the auctions around it. And that's called the epsilon ball around the A, okay? And for example, you can imagine that if I'm only interested in getting a epsilon optimal revenue, then maybe I don't need to have very fine-grained information about a bid. I can round all the bids up to multiples of epsilon, and that's still enough. And therefore, every sort of coarse version that first round bidders up to multiples of epsilon is going to also cover all the sort of finer grade auctions that make very detailed treatment of bidders' values. And that's the epsilon ball. Okay, with the epsilon ball, we know that, okay, if I estimate one auction actually cover everything inside the epsilon ball, and if I have a bunch of epsilon ball that actually cover the whole auction space, then I'm done, because all I need to do is going to find one representative within each epsilon ball, and I estimate the revenue of that representative accurately, and I do that for every single representative, then I'm done. So a lot of learning theory is concerning about, finding a epsilon net or epsilon covering of the entire auction space. And finally, after that, what we need to do is, okay, let's increase the number of samples by a factor that is proportional to the log of the number of representative, or the log of the number of the epsilon balls that you need to cover the entire space. And that's it. With that many samples, you can confidently say that I simultaneously estimate the revenue of every single representative accurately enough and cover everything. Okay, so well, in auction theory, this epsilon net has been constructed either explicitly or through some indirectly through concepts like VC dimension and several other learning dimensions. And I'm not going to touch those technical details, but every single tool from learning theory have been tried on this learning problem related to auction. And progress has been made, but tight bounds are still unknown after 5 years of research. Now, since 2019, the research focus has switched to the flip side. Instead of learning the auction, I just want to learn the value distribution accurate enough. And the logic here is that if I learn the value distribution accurate enough, well, I should be able to make accurate decision, okay? So in what sense we can learn the product value distribution? Now here we're going to consider the samples, M samples, and each sample being a vector with one value for each bidder, okay? Now we have touched upon the empirical distribution, which is the uniform distribution over the samples, okay? And according to learning theory, we want to estimate the revenue of different auctions by taking the average, and therefore it makes sense to consider this distribution. But from the context of learning product distribution, this does not make sense because, well, we have the prior knowledge that it's a product distribution, and just focus on this picture. If you look at the uniform distribution over these blue points, clearly it's not a product distribution, right? So if we have this prior knowledge, I should actually make use of this prior knowledge, and that should help me learn this product distribution more accurately. So that leads to a natural alternative, which we call the product empirical distribution, and saying that, okay, let's learn the final distribution coordinate by coordinate. And for each coordinate, I simply take the uniform distribution over the corresponding entries of the samples, okay? Now, visually, what it says is that I'm going to draw these dashed lines in each coordinate for each sample point. And I'm going to take all the orange points, which are the intersection of these dashed lines, and treat them as samples as well. And say that instead of taking the uniform distribution over only the blue points, let's take the uniform distribution over both the orange points and the blue points, okay? Now this has a few implications. Well, first of all, it just turns out that computationally finding the optimal auction with respect to a correlated distribution, like the empirical distribution, is a very, very hard problem, and versus finding the optimal auction with a product distribution, like the product empirical distribution, is computationally efficient. Now that's the computational aspect. Now from the information aspect, well, by including these orange points, I'm actually artificially increasing the number of data points that I have, right? Like imagine I have m-dimensional space, then by taking these orange points, I'm increasing my number of samples from m to basically m raised to the power of n, okay? So essentially I have an exponential increase in the amount of data that I have, and therefore I have more information about what's going on. Okay, so I'm going to go through the next few slides a little bit quicker. So here's what we can say about learning product distributions. We know exactly how much data is necessary and sufficient for learning a product distribution accurately, okay? So if D is n-dimensional product distribution, and let's say each dimension can only take k values, then we can show that, okay, with n times k over epsilon square samples, and if you construct the product empirical distribution from these samples, then the distance between your true distribution and the learned empirical distribution is at most epsilon, okay? So this amount of sample is both sufficient and necessary. And well, let me skip this and actually turn to the next slide. And because in this slide, we only talk about finite support distribution. And when I started with like bidders can submit any bid that they like, right? So it's not actually a finite support distribution. So it would be nice to get rid of this. But the problem with that is that if I look at a continuous distribution, let's say a uniform distribution between 0 and 1, and when I have an empirical distribution, which is a uniform distribution over a finite number of sample points, which is the discrete distribution, then a lot of the standard notion of distances between distribution would say that, okay, these two distributions are infinitely apart from each other. The distance between them is basically the maximum possible value. So what we identify here is that, okay, even though when D is a continuous distribution and D is the product empirical distribution, we cannot directly say that D and E are close by standard distances. We can say that E is actually sandwiched between two distributions called D plus and D minus. And actually these sort of upper bound and lower bound distributions are actually pretty close to the true distribution. And I can explain what these things are in just a picture. So here I'm going to assume that the real distribution is just a uniform distribution between 0 and 1. And if I plot the CDF, it's going to be just this diagonal line from 0, 0 to 1, 1 of this distribution, okay? So this blue line is going to be the CDF function of the true distribution. Now with some samples, and look at the CDF, the discrete distribution is going to be a step function, right? It stays at 0 until I hit the smallest sample point, and then the CDF is going to jump to 1 over m. And when I hit the second smallest sample point, it's going to jump to 2 over m, and so on and so forth. And if I have enough sample, I can imagine that this step function is going to jump up and down near this diagonal line, okay? So that's the CDF of the empirical distribution. And standard concentration theory, standard tools from statistics is going to say that, okay, it's never going to deviate too far from the blue line. In particular, they're going to give us some upper and lower bounds on how far these green lines can jump up and down, okay? Now, these upper and lower bound themselves can be viewed as functions mapping from the value space to numbers between 0 and 1, and therefore they actually correspond to the CDF of some distributions. Okay, and this dashed blue line are actually my D plus and D minus. And by design, well, the empirical distribution is going to be sandwiched between these two distributions. And then also by rather elementary calculation, you can show that, okay, D plus and D minus are rather close to the original distribution. Okay, this is the last slide, basically the final touch that will complete the picture of this whole theory for learning optimal auction from data. So if we take a step back and think about what we're doing, right? Like from data, we construct some kind of empirical distribution, and we're going to choose the optimal auction according to that empirical distribution, right? And then we know that the true distribution is in some sense close to the empirical distribution, but not quite, right? So in essence, we're saying that, okay, what if I run the optimal auction of some distribution on some similar but not exactly the same distribution? How much error do I get out of here, right? Now, if you inspect this question, and if you look at the simplest case of selling one item to one buyer and essentially just set a price and see if the buyer takes it, you will realize that overestimation and underestimation has very different effect. If you overestimate the bidder's value and therefore overprice a little bit, the buyer can actually go from buying the item to not buying the item. And when the buyer does not buy the item, your revenue drops all the way to 0. Now, on the other hand, if you underestimate the buyer's value and let's say lower price by 1%, okay? Whenever your buyer is going to buy in the original optimal price, he's still going to buy here, right? Because your price is lower. So at worst, your revenue only dropped by 1%, okay? So in this sense, in the single buyer, single item case, actually lower pricing and underestimating a buyer's value distribution is much safer, much more robust than overestimating a buyer's value distribution. Now, if you try to formulate this into some kind of a theorem that you want to investigate in broader context, then that is basically asking, is auction revenue strongly monotone in the sense that if I run the optimal auction of some distribution E on a quote-unquote larger distribution in some sense, is it the case that I get at least the optimal revenue with respect to the smaller distribution E? Because if I run it on E, I get that optimal distribution. Now that I run it on larger distribution, maybe I can expect at least as much. If this is true, that actually points to a slightly different but more robust learning process. Instead of constructing the empirical distribution, which eventually converge to the optimal, the true distribution, now I want to learn a distribution that is still close to true distribution, but at the same time being smaller. I want to approach it only from below, but not from above, okay? So that I get more robustness, okay? Now it just turns out that in a sequence of work, as I mentioned, for one item, one buyer, that's folklore. About 8 years ago, 7 years ago, we showed that, well, for one item and multiple buyers, this is also true. And just this year, we show that, well, for multiple homogeneous item, meaning that multiple copies of essentially the same item, then this is still approximately true. And it is still unknown that, well, if I have different kinds of items like apples and oranges, then whether this is approximately true, and maybe one of you in the audience can help me solve this, and that will make progress both on this conceptual question and also contribute to, well, more robust way of learning optimal auction from data when I have heterogeneous items. Okay, I'm already overrunning, so let me stop here and maybe take some questions from the audience.